Okay, so we have one more part of this section that I want to go over with you guys, and that's about mathematical models. So a formula is a statement of equality that uses letters, so variables, to express a relationship between two or more variables. The process of finding formulas to describe real-world phenomena is called mathematical modeling. So mathematical modeling is the process of using math to model the real world, right? It could be things in business, it could be geometry problems, area, perimeter, things like that, and so on. So there's a ton of applications. Math is everywhere. And these models can be used to help us make predictions, to make decisions, and just explain how the world works. Such formulas, together with the meaning assigned to the variables, right? So every letter or every variable obviously has a specific meaning in that formula, are called mathematical models. We say that these formulas model or describe the relationship among the variables. So we actually saw a previous example of a mathematical model already, although we didn't use that terminology. So we saw in a previous example that with an American man born in 1950, they have a life expectancy of 65.6 years. And we also saw that it increases by approximately 0.16, so 16 hundredths of a year for each subsequent birth year, right? So if you were born in 1951, you would theoretically live an extra 16 hundredths of a year. We can use variables to express the life expectancy E for an American man born X years after 1950. Okay. So because we're talking about years after 1950, notice we're using our starting point here of 1950. So this was the approximate age, so the life expectancy in 1950. So again, that's our starting point. And then here we have our change, right? So we found that it changes by 0.16 of a year, so 16 hundredths of a year, with each additional year of birth, right? So born in 1951 or 1952 and so on. So this is our mathematical model. And this is an example we've seen before. So some of you may be more or less familiar with it if you've had algebra already. So you may be familiar with something like y equals mx plus b. So we have this linear equation here, and m we have seen previously was our slope or our rate of change. And b was what we called the y-intercept, but it really was that starting point. So for those of you who are not familiar with this notation, I don't want you to worry about it. You don't need to know it, but I know there are students who have seen it before, so I just want to make that connection that we're using the same type of formula. So you have that starting point that gets added in. So here our starting point is 65.6, and then you take your variable x and you multiply it by the change. And that's a pretty standard mathematical model. It's a linear model because the data forms an approximate line as it's increasing over time. Okay, so let's look at one more example. Let's see if I can zoom out a little bit here. All right, so here's example 8, and again, there's so many graphs, I just copied them right from your text so I could talk about them easier on the screen rather than trying to bring the text out with my document camera. So we have a bar graph here in the figure, and it shows the average cost of tuition and fees for public four-year colleges adjusted for inflation. So we're looking at the average cost of tuition and fees. And again, this is at four-year colleges. Estimate the yearly increase in tuition and fees round to the nearest dollar. So again, we're estimating here, we're not going to get an exact value. And we're looking for a yearly increase. So we're looking for that change. How is the tuition changing? Now, if you look at your graph here, yes, I could look at 1 year to the next and say, okay, well, how is this changing, and see if I could figure out a pattern, right? But that's really difficult and really cumbersome to do. So what we can do here for part A is we take the last amount and the first amount. It doesn't have to be high or low. It could be a decreasing graph or a little bit all over the place, but usually we take the last one and the first one. And we're going to find that change. So again, if you've seen this notation before for m of slope, that's really what we're finding here. But you can think of it as finding your rate of change. And to do that, what we're going to do is we're going to subtract our two heights. So these would be our y values, right? This is our y-axis goes up and down, and your x-axis goes left to right. So what we're doing is we're subtracting our y values, and then we're going to subtract our x values. And you just want to make sure you do it in the same order. So if I start here with the 9,410, I'm going to make sure I start here with the year. Okay, now let me just get out my values. So I get 6,061 over 16. Now, you definitely have to round here. So you're going to use your calculator. Let me see what I already got. 378. 0.812 and so on. That's going to keep going. Okay. It does ask us to round to the nearest dollar. So I'm rounding to the nearest dollar. This next value is big. So I'm going to bump that up from 8 to 9. And I see that it changes at a rate of about $379 per year. And again, it is an estimation because not every year is exactly 379, right? But we're looking at kind of like the starting and the end points and taking the average there. Not so, I shouldn't say that, not an average, but an average rate of change because we are using subtraction. Now, the second question asks us to write a mathematical model. Now, to do that, you can kind of see, I know it's hard to see because it's a bar graph, but if you kind of look at the heights of the bar graphs, you can see that it's almost a straight line, right? Not perfect, it's not exactly a straight line, but it's almost a straight line. So when we have that straight line pattern, what we do is we use that formula I just showed you. So you're using this idea of this y equals mx plus b. So what's going to happen here is, in this case, we're talking about our tuition, right? And we're doing X years after 2000. Let me scroll down. So what's happening here is we're starting at 2000, year 2000. So that's key. Oh, sorry, guys. There we go. So we're starting at the year 2000. That's really important. Where do we start? Okay. So when we create our formula, here we're going to use T for tuition. And we're going to take our change. So this is our change. And this is our starting point. So our change here is 379. And that would be in years. And we're using, it was told up top, X for years. And then we're adding that with our starting point. And our starting point was this 3,349. So this is what our model looks like. Now, if you wrote it in the other order, so your textbooks likes to put that starting value first, that's okay too. But what you should be noticing, right, is you have some sort of variable is equal to a starting point plus our change times X. X is usually the other variable, but it could be different, right? It could be a different letter. So you kind of have this general formula when you have this overall kind of linear, this line shape. Now, our last part asks us to use the mathematical model to project the average cost of tuition and fees at a public four-year college for a school year ending in 2020. Now, be careful here. Remember, X would be the number of years after 2000. So if we're going to 2020, then the X value that we're looking at is just 20. It's 20 years later. So we're plugging in an X value of 20, not 2020. So you want to be careful here. We're told that it's years after 2000, so it's 20 years later. So for part C, we're going to take that formula, that T equals 3,349. and we're going to add it to that 379 times 20. So our x value is getting replaced with 20 here. Now, when I multiply that by 20, so I'm just looking at my notes here, I have the 3349, and then this piece here is going to become 7,580. And I finally get that my tuition in 2020 is projected to be almost 11,000, right? Around 10,929. Now, this is an estimation, right? So we're using what has already happened to estimate what's going to happen in the future. And that's a really common thing to do in mathematics when we're modeling. We do want to be careful though, and this actually comes down here to model breakdown. Models, if they're constructed in a good way, right, if they're done correctly, are amazing. They can give us so much information about the world and what we think is going to happen. They let us make predictions so that we can, make better decisions. But we do have to be careful. And that one thing is that we cannot predict too far into the future. So here, when we did this example, we were projecting 4 years later. That's not that far, right? So going out 4 more years. But if I was going out 40 years later, that's much too far, right? That's going way far away from my model. And in 40 years, things can drastically change. So you do need to be careful that way when you make predictions. You can go a little bit outside the model, but you shouldn't be going too far. So even 10 years may be too far, right? It really depends on the data that you have and how far out you think you can go, right? So it's going to depend on the model, but when in doubt, err on the side of caution, right? So don't go too far out in your model to make predictions, or else what's going to happen is your model may break down over time. So things will have changed too much that the data becomes too old. It's not current anymore, so you need new data to keep more current.